So, hello again students, and welcome to a new nugget on biomass for energy. Today we will have a look at how biomass is harvested and collected and what to think about during these operations. We will also talk about historical data and how they can be used to estimate the probable yield. One of the most important differences between fossil energy resources and biomass is that fossil energy resources are generally concentrated. Though brown coal mines often extend across large areas, are the amounts of energy per area unit much bigger than those from biomass. But brown coal, or lignite, is still considered inefficient for transport. So what about biomass that has an even lower heating value and an even lower energy density? Let's first do the very roughest estimate of the maximum biomass yield per area unit. You know that the incident solar radiation outside the atmosphere is only about 1.4 kilowatts per square meter. And then you know that about half that is absorbed on its way through the atmosphere. So at the equator, midday on an absolutely clear day, may the incident sunlight at ground level reach about 800 watts per square meter. Plants tend to stand up and leaves move and orient themselves to maximize the irradiation, so a total absorption about 10 kilowatt hours per square meter and day can be reached around the equator. This value is extreme and not representative, and then biomass growth is usually not limited by irradiation anyway. Instead, the limiting factors tend to be soil quality, precipitation, and other factors. So reasonably representative biomass growth rates may be set at about 5 to 20 metric tons of dry substance per hectare and year. In case you need a brief repetition about solar energy and photosynthesis and you do not want to go back to the material from lesson 1, I would suggest you have a look at the home page of a company called Fondriest. If you go to their Learning Center and click your way into the page about parameters and then continue into the sub-page about solar radiation, you will find quite an interesting text there. The information in this page is non-commercial, though the company, of course, would like you to buy their metering and monitoring equipment. So let us now do another rough estimate. Assume we have a field 1 hectare to harvest. The field is square, 100 by 100 meters. The combine harvester is a bit more than 8 meters wide, and it is run back and forth. So it has to run 12 times to cover the field. And then it has also moved 100 meters along the field. So let us assume that it has run a total of 1.5 kilometers at full speed, which is 6 kilometers per hour. That means it has been running 15 minutes. The engine is well above 400 horsepower, so let's say 300 kilowatt. And then the total energy required is 75 kilowatt hours. Now, this is of course the extreme minimum. But even if we multiply by 10, will you realize that the energy input for the harvesting operation is less than 10% of the total energy contained in the crop? You will also realize that the actual extraction is never 100%. Just look at Table 1 in Chapter 2.2 in the Busy-Plan Handbook, for example. In this example is the crop a straw, and from the table you will see that some 40–50% is more reasonable. Finally, you will also realize that this is only half the work associated with the harvesting operation. For straw, will the next operation be baling, which takes place at a later instant. And a similar estimate can be done for that. You will generally want the straw to stay in the field for 1 or 2 heavy rains so as to wash out the chlorine. and that is why the baling will take place at a later instance. For a forest felling site, there will again be two operations to bring the material to the roadside windrow. First, there is the harvester felling the trees and doing the debranching and cutting. Then, after a few months, comes the forwarder to collect the material and build the windrows. Similar estimates as the one above can be done for these operations. Generally speaking, in-field operations, and the same holds true for operations at forest felling sites, tends to require an energy input about 5% of the energy represented by the harvested dry substance. It must never exceed 10% because then it's a result of a bad planning. This is a significant post in the total energy balance, and good care must be taken to optimize the handling and to avoid any unnecessary energy losses. The necessary amount of energy input compared to the energy of the material is the relevant measure of economy. Included in the harvesting and collection operations is typically at least one operation to increase the energy density of the material. In case algae have to be transported from the farm to a digester plant, flocculation and maybe even centrifuging may have been done prior to loading the slurry into a tanker truck. Animal dung will be drained prior to transport. Wet dung with urine will typically not be transported, or, if transported, will be pumped. For straw or corn stover or other agromaterials, it will have been baled prior to transport. For forest residues, will the material be chipped when loaded from the windrow into the road transport truck. Once the material is on board the truck, does the next part of the supply system start. In the previous nugget, I suggested a simple method to plan the energy supply system for robustness. The suggestion was based on the fact that for a long series of independent random variables will the statistical distribution successively approach the Gaussian distribution. This distribution is also known as the normal distribution. The distribution is fully described by only two numbers. These are the mean value and the standard deviation as shown in this slide. The formula for the Gaussian distribution is shown at the bottom of the slide. You will notice that in this formula the variable is normalized. The variable is marked by a red ring. The value is thus the distance from the actual value, x, to the mean value, x bar, expressed in a number of standard deviations. And that is why the distribution always looks the same. Here is an example in which the mean value is an annual yield of 15,943 tons and the standard deviation is 2,077 tons. The diagram extends across 8 standard deviations, 4 below and 4 above the mean value. And the area underneath the curve will represent 100% probability. The yield will not be less than about 9,000 tons and it will not be more than about 23,000 tons. From this curve we can now read that the probability for a yield about 13,000 tons is just about 15%. And because of symmetry, the same holds true for a yield of 18,900 tons. We can also see that the probability for a yield about 10,000 tons is less than 1%. And the probability for a yield about 21,000 tons is about 2%. But as a planner, you are not interested in the probability for a specific yield. What you are interested in is instead what is the total probability that you will run into a fuel shortage. So you will have to do a little more than just to plot the curve and read from it. In this slide, the white part of the area underneath the curve represents 25% of the total area. So the total probability that the annual yield will be less than about 14,500 tons is 25%. Or, if you wish, there is a 75% probability that the annual yield will be at the very least 14,500 tons. So the trick is to find a simple way to evaluate the integral. To do that, we will now make use of the classical approximation developed by Cecil Hastings at Princeton University and published 1955. It may not be the best one, but it is simple. The calculation consists of 4 steps once the mean value and the standard deviation are computed. First, you have to calculate the normalized variable. Then you compute a help parameter t. You will notice that this parameter t has to be computed using the absolute value of the normalized variable. The reason for that is that the approximation is basically valid only for positive function arguments. So to make it general, you have to make use of the symmetry of the distribution and guarantee that the parameter t is always non-negative. So once you have t, then you compute the distribution value for the normalized argument x sub norm. Finally, compute a help function f using the parameter t and 5 constants. The help function, as you see, is a simple polynomial. The values for the constants in the polynomial are shown in the slide. So by now you have 2 values. You have the probability p and you have the help function f. Again, you have to consider the fact that Hastings' approximation is strictly valid only for function arguments bigger than the mean value. So now you have to separate 2 cases. If your function argument x is bigger than the mean value x bar, then is the normalized variable x sub norm positive. In this case, is the original approximation from Hastings valid, and the integral value is computed as 1 minus p multiplied by f. If your function argument is less than the mean value, then is x sub norm negative. In this case, is the original approximation formula not valid. So for this case, is the sought integral evaluated only as p multiplied with f. Now make yourself a calculation spreadsheet to do this. To test it, I have supplied a series of 17 values. These values will give you a mean of 15,943 and a standard deviation of 2077. So this is exactly the data set I have used to produce the curve we have been looking at ever since slide number 10. You will see from the histogram that the distribution is far from Gaussian, and that is the risk with this method. In a case like this, may the implicit assumption made by this method produce false results. And that is why it is so important that you collect a long enough series of time data. But we will not go into the details of statistics. Now use the data set provided just to check that your calculation spreadsheet works properly. With the data provided here, you should be able to compute the integral, setting the integration limit to 14,541.5 tons. And doing that, you shall find that the integral is almost exactly 25%. Once you have the calculation worksheet running, you are finished with the theory session of this nugget, and you will be ready to proceed with the homework.